Now, of course, the first step in analyzing the circuit will be to derive the governing equation for the circuit, and the following step will then be to solve that equation. So to derive the appropriate equation, we need to define a few more variables in our problem that we can solve for. These are all of the givens to us in the problem. What we don't know in this problem, for example, is the current flowing through the circuit at any time t. So I will define that here as I. And of course, by Kirchhoff's first law, we have that same current I flowing around the entire circuit. The second thing that we don't know yet and need to determine, of course, is the charge on the capacitor. Now, for the current, as soon as I drew this arrow here, I've defined a presumed positive value for current. I made this choice because it seems sensible that current would come out the nominally positive side of the EMF. Similarly, I have to decide the plus and minus plates on my capacitor, so I will choose as so. Again, thinking that, well, likely if the current were to flow this way, that would make the upper plate of the rightmost plate of this capacitor more positive. And then I can define, now that I have given the sign convention, my second variable in the problem. My second unknown is the charge on the capacitor. With my unknown physical descriptors of the circuit defined, and the circuit also and its elements specified, I can now derive the equations governing the circuit. We've already taken care of Kirchhoff's first law, of course, because there's only a single loop in this circuit, so there is only one current flowing around through all of the elements. They are all the same. The second Kirchhoff's law, of course, we are going to be using now the effective law because we are dealing with a circuit with an inductor. But after a while, once we've gotten used to the idea that these are effective voltages, we can just start to think of them in terms of circuit analysis as regular voltages. So I am not actually going to continue writing the quotation marks everywhere. So when I apply this second Kirchhoff's law, I'm going to make a loop around my circuit. I will choose this point here as my starting point, and I will loop around the circuit in this given direction. So as I go around my direction then, the first thing I come across is I go across the EMF. And because I'm going from minus to plus, I would of course choose the plus value for the EMF at that point. And that EMF, remember, is a function of time t. Next, I go across the inductor, and that will be the governing equation for the inductor is plus or minus L times di dt. And I have to choose my signs here carefully. Notice that I need to decide which is the upstream and downstream sides presumed for my inductor. And because I have my current presumed in this direction, the presumed upstream side here would be what I'm labeling plus, and the downstream side would be what I'm labeling minus. And in this case, as I'm adding my effective voltages around my circuit, I am going from plus towards minus across that inductor, so minus would be the appropriate choice. Next, after I've gone through the EMF and the inductor, I go across the resistor, so that will be a plus or minus I times R. Once again, I should be careful with my signs. My presumed current is flowing down through the resistor, my presumed positive flow for current. So the presumed plus will be on the top, minus on the bottom. So I'm going again from plus towards minus. That will be the negative sign choice. Finally, I come to my capacitor C. As I go across the capacitor, of course, we know that's plus or minus the charge divided by the capacitance. And in this case, yes, once again, I'm going from the plus plate of this presumed plus plate of the capacitor to the presumed minus. So the choice again is negative. Now, that then and of course all of this must give me 0, so let me put my 0 in at the beginning of the equation. Very nice. Now, that gives me one equation. Unfortunately, we've got two unknowns in here, the current and the charge on the capacitor. What I highly recommend, actually, is that every time you write down a Kirchhoff loop where you go across the capacitor, that right away, before you forget about the free available equation that comes with every capacitor, the first time you use a capacitor, make sure to include the current charge relation for that capacitor. So let me write that down right next to this one. So for my capacitor, the governing equation, the second free equation for any capacitor, of course, is that the current flowing through it, which in this case is I, must be plus or minus the time derivative, right? Because current is charge per unit time. And what we have to always be careful about is our choice of sign. In this case, the sign conventions for my current and my charge are such that a positive current would be pushing positive charges onto the positive plate of my capacitor, increasing the charge Q. So when the current I is positive, dq dt would be an increasing function, so dq dt would be positive, and for those signs to work out appropriately, I would have to choose the plus sign there. Okay, now we actually do have our two equations and two unknowns. It's time to solve these equations, and the best way to solve two equations and two unknowns, as you all know, is simply to substitute one of those equations in for the other. So that's what I intend to do. I'm going to do a few steps of algebra at once here to save a little time, so follow with me carefully. I'm going to rewrite the K2 equation. Now this equation, notice, has minus signs for all three terms, for all of the circuit elements except for the EMF. So I'm going to say that the EMF equals, and then I'm going to move all of these other terms to the other side of the equation, where they will all appear then with positive signs. As I write them down, I'm going to make a second step, which is substitution of what I know what the second equation is telling me, the current. I'm going to substitute that in while I'm writing the equation. So I will have one equation solely in terms of charge Q. So let's try this. So this term, the inductor term, goes to the other side of the equation with a plus. It becomes L times di dt, but I itself is dq dt. So I have d by dt of d by dt of q. That is two time derivatives of q. So this is d squared q dt squared, the second time derivative of q. The next term is the resistor term. I have, then it will become plus I times R. R is the constant here. So just as I had written L first, let me write the constant part first. So it comes over with a plus sign. It's R times I. But remember now that R times I, but I, once again, is plus dq dt. So that becomes R times dq dt. Finally, I have the capacitor term. That goes to the other side of the equation. It's already written in terms of Q, so it becomes plus, and I can then leave it in terms of Q. In fact, here, let me write them all in the same way. So I have the constant prefactor 1 over C, and then times Q. So this, then, is the equation that I have to solve.